One final thing I want to talk about is that this definition of activity and activity coefficient, this is what's considered, this is what we use for the solute. So, sorry, not solute, the solvent. This is for, if we have a mixture of something where the thing that's present in larger quantity, right? And just as a reminder, I forgot to write this, is that the activity coefficient we call gamma, same as the fugacity coefficient, because that's not confusing. But it's this ratio of the activity to the ideal behavior. Now so this works really well for the solvent, the thing that's present in higher amounts, because as it approaches behaving like a pure substance, we should get ideal solution behavior. But on the other hand, we also need to think about a solute that's present, and this will prepare us for chapter 25, where we're going to be talking about solutes dissolved in solutions and how we deal with that thermodynamically. And for a solute, what is considered ideal behavior is a little bit different. And so to illustrate this, we have a law, that's sort of an empirical law called Henry's law, which says that Pj for a solute, right, so this is for our thing that's present in small amounts. So we have a small amount of component J here. The vapor pressure of that component will start behaving, start to have a linear trend to it, but it won't match the mole fraction. So the vapor pressure of component J approaches some constant that we call Kh of component J, times xj, right, times the mole fraction of j. And here the difference is, instead of it's as xj approaches 1, it's as xj approaches 0. So whatever's present in smaller amounts in our solution, its vapor pressure doesn't go as the mole fraction, right? If this was strictly by Raoult's law, we would expect this to be xj times pj star, but instead it's not, right? This will be true for the solvent, but not for the solute. For the solute, we have this other constant Kh. Now, this is an empirical constant. This is something you have to measure to be able to determine what's going on here. I'd like to illustrate this graphically to show sort of what I mean by this behavior. The consequence of this is that the activity and activity coefficient that we define for the solvent is different than what we define for the solute, and we'll go into that more in chapter 25. And there's different standard states we can define things relative to and whatnot. But basically, we're going to get something where the activity is equal to, instead of Pj over Pj star, we get Pj over the Henry's law constant, Kj, Kh. Okay. But let's illustrate what I mean by Henry's law, and I'll do this with a PowerPoint slide here. Okay, so this is looking at a non-ideal solution, right? So if this behaved according to ideal solution behavior, let me see if I can get I'm trying to get a laser pointer. There we go. Okay, so if this behaved ideally, then it would just follow this straight line here, and it would behave according to Raoult's law. So we'd have a linear trend with respect to the mole fraction of, in this case, an alcohol. I think this is an alcohol-water mixture, if I remember right. And what we see is, as we get to really high concentrations of our alcohol, as that approaches 1, we do see this does behave according to Raoult's law in the limiting case, right? We have Raoult's law behavior. This follows a linear trend out here. Now, according to the Gibbs-Duhem equation, if the chemical potential, which is directly related to the vapor pressure, if that behaves in a linear fashion at high values of x, right, then we should also see a linear trend for the other component, right? It should follow the same functional form according to the Gibbs-Duhem equation. Now, that would be the left-hand side over here, but that would be looking at our other component, right? And I think that would be water in this case, if I remember right. Down here for our solute, right, whatever's present in lower concentrations, we see it doesn't follow Raoult's law. Now the solvent, whatever the other component is here, would be following Raoult's law, similar to what we're seeing over here. But down here we don't see that behavior. Instead, what we see are linear trends, right? There are linear trends as we approach zero. And this is Henry's law. This is the limiting behavior as we go to lower and lower concentrations of our solute. It starts having linear behavior because the solvent is approaching Raoult's law. And so these are direct consequences of each other. If the solvent is behaving according to Raoult's law, the solute will also have that linear trend. It just won't match the mole fraction. Instead, it'll be some other constant. That's the Henry's law constant that is multiplied by the mole fraction. So we still get this linear trend, but it doesn't follow Raoult's law. It follows Henry's law instead. So hopefully that is a useful visualization of why we what's going on here. And these are sort of two sides of the same coin. According to the Gibbs-Duhem equation, these chemical potentials, which again are related to the vapor pressures, are behaving, follow the same functional form. So that's why they're linear for both of them, but the coefficients are different. Right? The coefficient here is just the mole fraction, but here it's some other constant. So for chapter 25, when we start looking at solid liquid solutions where we have a solute present in the solvent, this Henry's law behavior is going to become very relevant when we're thinking about activities and activity coefficients and how we can find those for those types of solutions. Take me just a second to find the stop button.